Okay, so we're going to talk a little bit about some models of population growth. In particular, we're going to get to the logistic model. But first, let me talk about a simpler model that's probably too simple, and I'll talk about why. So the simple model that I'm going to talk about is that the birth rate of a population is proportional to P. P is the population at any given time. And the death rate is also proportional to P. So this suggests a differential equation where the rate of change of my population is, well, we could say this is like the rate coming in minus the rate going out, and the rate coming in is the number of births. And we just said that the birth rate is proportional to P. So I'm going to make up some constant beta and say that like beta is the constant of proportionality for the birth rate. So the birth rate is beta times P, so it's proportional to P. And then the death rate, so I'm going to subtract the rate coming out, and in other words, that's the death rate. And that's also proportional to P with some different constant that I'll call delta. So this is an easy differential equation. I'm not really going to show the work. This is, so I can factor out a P here, and then I just have a constant times P because beta and delta are both constants. So this is a separable differential equation. You can solve it at home, and I'll just tell you what the answer is. P of t is this. So if beta is bigger than delta, then this is a positive number, and this is telling us that the population grows exponentially. And if beta is smaller than delta, so the birth rate is smaller than the death rate, of course the population is going to go down, and that would be exponential decay, like e to the negative number times t. And so I would say this is a bit too simple of a model for population growth because, well, one way of thinking about it is to just look at what the solution is. It's not really believable that that the birth rate, say if the birth rate's bigger than the death rate, then the population is really going to grow exponentially forever. Like in the long run, that's not possible. It's unless we're going to start populating other galaxies and stuff. On Earth we have some maximum capacity. It's up to debate what it really is, but it's really not believable that we're just going to keep having babies after the Earth is just full. So this model, looking back at the assumptions that we made, it's probably not reasonable to just assume that the birth rate is always proportional to P, like assuming that people just have babies, or whatever. I guess I keep saying people, but this could be a population of animals or plants or whatever, that they just continuously have babies at the rate that they exist. Realistically, as conditions start to get worse, or as we start to face more competition with other members of our species, the birth rate does go down. So let's talk about a slightly more realistic model of population. So the birth rate's going to go down. So instead of being just beta times P, I'm going to introduce this new thing. So I'm introducing a new constant. I guess I'm just using the Greek alphabet, so I chose gamma. So instead of just a beta here, I wrote something that gets smaller as P gets bigger. So that's the minus gamma times P. And then the death rate really is realistically, that's not a terrible assumption that it's proportional to P. You know, you have members of the population kind of going around and variously getting diseases and falling victims to accidents and whatever else happens to make them die. And you know, at any given time, everybody has about the same chance of dying. And so the death rate is probably really is going to be proportional to P. So we're not going to change that part. We're changing the birth rate. Anyway. Of course, this suggests a new differential equation, which is similar. It's just the new rate in minus the rate out, which is in the same way as before. So we can do a little bit of algebra, factor a p out of this. And this has probably a bit too many constants floating around. I've got beta and delta and gamma. Let me kind of simplify things. We can imagine pulling a gamma out of this, because gamma is just a constant. And so I guess I'm going to rewrite it here. And I guess k is just the same as gamma. But whatever I get after pulling a gamma out here, this is also just a constant, and I'm going to call that m. So I get a differential equation like this. Still, it has two constants, but that's better than three, I guess. So we have two constants, k and m now. Looking at it this way, m is often called the maximum capacity, just because if you think about it, if p is smaller than m, then that means p is going to increase, assuming k is positive. We assume k is positive. So this is telling you that dp over dt would be a positive number. P is positive, that's the population. And if p is smaller than m, this is also positive. So everything here would be positive, meaning that p is going to keep increasing. But when p starts to get closer to m, this term gets close to 0, and so p is not going to be increasing very much. So this tends to level off when p gets close to m. And we'll actually see that when we solve it. So let's make this a initial value problem by introducing an initial condition. Let's say the population at time 0 is something that we'll call P0. And for us right now, let's assume that P0 is positive. That's a reasonable assumption for a population. And also that P0 is less than m. You can talk about this differential equation if P0 is greater than m, but for now, let's assume that P is less than, or that P naught is less than m. Let's solve this. So let's keep in mind, there's kind of a lot of letters going on here, but the k and m are constants, and the variables are p and t. This is a separable differential equation. Let me show you. I'm going to get all the p's on one side with the dp and all the t's on the other side with the dt. So, okay, so I'm going to keep the dp on the left. Anything with p's in it needs to move over to the left. So this stuff that's on the right would need to move over. So k could stay on either side. K is just a constant, so maybe I'll keep the k here. And there's no t's. There's a dt, but there's no t's. So I would call this separated. So integral sign, integral sign. This side is going to be very easy. This, this is just a constant, so this just turns into k times t. This side is conceptually not difficult, but it's going to be just a little bit painful. This is partial fractions, right? I can see, or keep in mind, the variable here is p, so I can see the bottom is factored. So what do? We take this and set it equal to something, something over my first factor. plus something over my second factor, and I'm going to figure out a and b to make this true. All right, let's go. So I'm going to clear the denominators. In other words, I'm going to multiply by p m minus p on both sides. On the left side, of course, that everything just cancels and I just get 1. On the right side, I have to be careful and distribute this carefully. So when I distribute this here, the p cancels, but the m minus p stays. When I take this here, the m minus p cancels, but the p stays. Okay? And the way I usually do this is I plug in convenient values of p, and the convenient values are something that makes one of these terms disappear. To make this disappear, I would plug in p equals m. That would give me 1 equals, this is gone, b times m. So we just figured out b. So, okay, I did that by making this disappear. Let me make the other one disappear. So I plug in p equals 0. I get 1 equals a times m. So a is also 1 over m. And we just figured out our a and our b. So let's go back to, maybe I'll put a star here. Let's go back to that equation. So star becomes, let's see here. So this turned into a over p. Okay, here we go. A over p, where a is 1 over m, plus b over m minus p, and b was also 1 over m. So that's the left-hand side of star. And the right-hand side, well, this is so easy. This is just k times t plus, I'll put a constant. And we're still working on the left-hand side. But we're making progress. Okay, here we go. So this is an integral with respect to p, and m is a constant. So this one is easy. This is just 1 over m, natural log absolute value of p. And this is 1 over m, natural log absolute value m minus p, but because we have this minus in front of the p, that's, well, I could just stick a minus sign in front of the whole thing, but I would call it 1 over negative 1. That just makes it negative. Okay, so the antiderivatives are over. And, right, so let's assume, and this is not a crazy assumption, that this is really justified. So what's on my mind right now? These absolute values. As soon as I write these absolute values, I'm looking for a reason to get rid of them or ignore them or figure out what they do. So I'm thinking about whether p is positive or negative, and I'm thinking about whether m minus p is positive or negative. Keep in mind, this is the real world, sort of, or we're pretending this is the real world, right? So p is a population, so p is going to be positive. Also, m minus p, as we sort of talked about, m is like the maximum capacity, and we're going to talk about the situation where the population is less than the maximum capacity. In other words, m minus p is positive. So let me rewrite this. 1 over m natural log p, because these absolute values don't do anything, minus 1 over m natural log m minus p. Like that. So we would like to solve this for p. This is like an implicit solution. But it would be nice to really have a formula for the population. Like you tell me how much time has passed. I would like a formula for what is the population after that much time has passed. Also, we should keep in mind, we did have an initial condition, so we should be able to figure out the constant that we introduced when we did an antiderivative, c. So let's talk about those things. Let's solve for p. So it's a small miracle that we can actually solve this for p. I've got p in two different places. Luckily, I can combine these natural logs. So I can pull a 1 over m out of both. And if I pull a 1 over m out of both, let me just cover these up with my fingers. I've got a log minus another log, and I can use the magic of logarithms to turn this into log of a fraction. Right, if I do log of a fraction, that's the same as the log of the top minus the log of the bottom. So it's like log of p minus log of m minus p. So it's like that. My goal is to solve for p, so let me get the m over. Well, how do I get rid of the natural log? I do e to both sides. Okay, now we're going to do a little bit of ugly algebra. I still have p in two different places. Let me multiply this over here. Let me distribute this. So this is my punishment for deciding that I wanted to show all the work, because this is, okay, so I do m times this minus p, and then I have to write this all again. I shouldn't complain, but I am. So it's like that. Want to solve for p's, let me get the p's back on the same side. In fact, let me start trying to go faster here. I'm going to get this term back on the left, and then I'm going to factor out a p. So I'm going to get p times, first of all, there's going to be a 1 there because of this p, plus whatever this, when I move this over here and pull a p out, I'm going to get e to the m kt plus c equals, this is still on this side. Finally, I can solve for p. I just divide by this stuff. Like that. And yeah, let's see here. How are we going to deal with this initial condition? right? We had an initial condition. Remember forever ago when we made the mistake of embarking on this problem, we had an initial condition. P of time 0 is P naught, and that should allow us to solve for C. What I don't want to do is use this for that, right? Like I could plug in P naught here and plug in 0 for T, but then I would have to solve that equation for C, and I have C in 2 places, and it would be doable, but I don't want to do it. Let's do something else. Let's use, so we have a bunch of equations that are all equivalent to this. Before we decided to, you know, like for this equation, in fact, every line from here down, it's all equivalent to that. So I could pick and choose whichever one of these I find to be most convenient. Let me actually pick this one, because my goal is to solve for C, and this is one where C is going to be very easy to solve for. So let me maybe call this something, double star. So I'm going to take double star and put in my initial condition. So my initial condition was this. So P naught goes in for P. Zero goes in for T, because that's this. So we just figured out C. Yeah, okay. So let me, I don't know, I'm tempted to do even more with this, but maybe I will stop here. So the solution to the logistic equation that we started is given by this, where C is this. That's one way of describing the solution. Yeah, there are even more models of population growth. This is, for whatever reason, a particularly popular one. But let me just go back to the setup here. It is reasonable to think that the birth rate should, that this should be decreasing in P, like this part, because, you know, as the population increases, there's more and more competition for resources and that type of stuff, and then members of the population just start deciding to have fewer babies. It's not necessarily going to decrease in a linear way, right? Like this in these parentheses is like a linear function. It's like it just depends on P. But you know, in reality, what if it was a P squared or some other power of P, or really this could be any decreasing function of P. So there are definitely other models of population growth, but this logistic one is one that we talk about a lot.